I've received a very excellent question, okay? So about the definition of this Platonic solid. So there is something wrong there. Okay, so let's take a look of this shape. So this is a tetrahedron, okay? So imagine you have two tetrahedrons, so two of them, and then you have the same shape here, you glue them together. Then you have what? You have got a new shape. This new 3D shape, it is having every side, every face is the same regular polygon. Am I correct? But then we don't consider this as a Platonic solid. So I think the definition of Platonic solid, we need one more thing. It needs that the shape is always symmetric if you look at each vertex. You change the looking from each vertex. So this is not symmetric in a sense that if you look at this vertex, it has degree 3. So it is joining 3 triangles together. But if you look at this vertex, this will have 1, 2, 3, 4. It is joining 4 triangles together. So this vertex and this vertex, they do not look alike. So there is an extra requirement that for a Platonic solid to hold, each vertex should join to the same number of faces. Okay, so all the faces should be regular polygon, and then all the faces should be the same. And then one more thing, each vertex is joining to the same number of polygons. So in that case, this is a Platonic solid. Okay, so once we have this one, then we can show that there are at most 5 of them. Okay, now let's talk about a new thing. So we are going to talk about how to do coloring of a map. So we are doing map coloring. So let's say this is a map, and each of these regions corresponds to a certain country. So there are country A, country B, country C, up to country F. Okay. Now in a map, the basic requirement we want to have is that if 2 countries are sharing a boundary, so let's say A and B, they are sharing a boundary, we should color them using different colors. Is that okay? So what is the minimum number of colors that we need to color a map? Okay. So we assume that this map is drawn on a plane. So in 1960, okay, so this result, 1976, so this is the year. So these 2 persons, Apple and Hacken, Appel, and this Hacken, they have shown that 4 colors is enough. So if a map is drawn on the plane, on the surface of a plane, okay, so 4 colors will be enough. Okay, but then this proof that 4 colors will be okay. It needs to use computers. Okay, it is because these 2 mathematicians, they have shown that all the possible maps are one of these 195 cases. So they have imagined all the possible situations, and the number of situations are what, 1,955 of them. So there are so many cases, okay, that a map can look like. So in that case, they ask a computer, they write a program and ask the computer to check for each case it is really true. We can color them using 4 colors. Okay, but then there are still a lot of mathematicians. They don't like this proof. It is because nobody can verify whether this proof is correct. If you want to verify this proof is correct, you need to verify 2 things: whether these are the only cases that we should consider, and also you need to check whether the computer has a bug or not. And the latter part is the most difficult thing. Although there are some further improvements in the recent years, so it reduces the number of cases into what, 1,476, but it is still a lot. Okay, so we are going to talk about this, but then we are not going to talk about 4 colors. So today we are going to talk about what happens if we are allowed using 5 colors. Now, using 5 colors will be much easier to prove. So we can easily show that 5 colors is enough. Now, one more thing. There is an emphasis that this map, we need to assume that it is drawn on a plane. Okay, if you have a donut, so you go to Miss Donut and then buy a donut, and then draw something on the donut, on the surface of the donut, then in that case, 4 colors may not be enough. So in that case, you need 7 colors, okay, rather than 4 colors. So here we are assuming that you have a map that is drawn on a paper. Okay, it's not like a donut shape. Okay. Okay, so let's do 5 colors. So to understand this, we need to understand an extra concept called dual graph. So first of all, planar map is related to planar graph. In what sense? Okay. So let me use a green one. Okay. So you imagine. So each word. So there is, for each country there is a capital. So this is the capital city of the country. So for instance, this is England, and this is the London, and then let's say this is U.S. and this is the Washington D.C. So you have a vertex that represents the capital city of each country, and then because each country they are what? They share boundary. If you imagine I'm driving a car, then I can travel from one city to another city by crossing the corresponding boundary between the 2 countries. Is that okay? And believe that there is a way that, so I can drive a car here, go to this boundary, and then enter this and go to this city. And believe that, okay, there is always a way that this route does not cross. Okay, so you can draw from this one to this one and then go to this one. Is that okay? You can draw from this one to this one and then go to this one. So what we are going to do, for each country, we are going to drive from its capital to the neighboring country's capital. Is that okay? So for this one, I need to drive to A, I need to drive to C, I need to drive to F, and also I need to drive to D. Is that okay? And then for D, I need to drive to this C, B, F, and then E. Is that okay? And for this E, I need to drive to this one, I need to drive to this one, and I also need to drive to this one. Is that okay? Is that okay? So in that sense, we have another graph produced, the green one. So let me copy the green graphs here. So the first vertex, it is an A, and then there is a vertex B, there is a vertex C, there is a vertex D, there is a vertex E, and there is a vertex F here. So that A is joined to B, A is joined to C, A is joined to F, B is joined to F, B is joined to C, B is joined to D, D is joined to C, F, E, and F. Is that okay? Is that okay? Did I miss anything? Yeah, this one. This 1, 2, 3, 4. I missed this one. Okay, thanks. Okay. So here, this graph, becomes a graph. This is a map. This is a graph. This graph is called the dual graph of the map. Dual means you look at it in a different way. Actually, this dual graph looks like a map itself. It looks like a map itself. And then you can draw the dual graph of this dual, the dual of this dual graph. You consider this as a map. Then there may be a capital city here, a capital city here, a capital city here. Is that okay? And interestingly, the dual of the dual, you get the original map, something like that. Okay? Look at it. So you have A, B, C, A, B, F. This looks like a country here, the green country. Then this is the capital city. Is that okay? Of that country. So a dual of a dual becomes the original one. Okay, but here, what we need to understand is that if there is a planar map, a map that is drawn on a plane, then the dual graph, we need to believe that it is a planar graph. Is that okay? So the roads you need not cross, so that you can drive from one capital to another capital in the neighboring country. If you're okay with this, could you please raise your hand? Okay, now this is the most difficult part. And if you understand that, then we can talk about everything on this dual graph. So what is meant by a coloring problem? A coloring problem means that originally I need to color the region, right? Here, I'm going to color the vertex. I want to give each vertex a color so that for two vertices that is joined by the edge, they should receive different colors. Is that okay? And then we are asked, how many colors do we need? So Apple and Heck can actually use this reduction and shows that 4 colors will be enough. And for us, we are not doing exactly the same thing because it involves a lot of cases. So we are proving that if a graph is planar, then 5 colors is enough. We need only 5 colors to color the vertices so that all the neighboring vertices receive different colors. Is that okay? If you're okay with what we are going to do soon, could you please raise your hand? Okay, good, good, very good. Okay. Eh? Okay, now So let me recall a theorem that we have proven before. This is going to be important. Okay, so we have, let me see. Okay. Okay, let me see. Excuse me, I need some time to recall this. So first of all, we have this result if, so this is the corollary. If V is greater than or equal to 3, then what? Then E has to be, so this is, then E has to be less than or equal to 3V minus 6. So this is a result for planar graph. So we have proven this result long time ago. Yeah, not long time ago, last time, when we are saying that a graph cannot have many edges. If a graph has too many edges, like a K5, it has 10 edges. Then much more edges than 3V minus 6, then this cannot be planar. Is that okay? So for any planar graph, this has to be satisfied. And from this theorem, we can actually show that in any planar graph, we can find at least one vertex at least one of the vertices will have degree less than or equal to 5. Okay? So this implies this one. Why? The reason is that we can prove by contradiction that this is correct. So we are claiming that in any planar graph, so let's look at that one, we can always find certain vertex that has degree less than or equal to 5. Yeah. In the above case, all the vertices have degree less than or equal to 5. And for this case, so this is a planar graph that we have tried earlier today. Then this vertex has degree 4, less than or equal to 5. Is that okay? Now the reason is that if every vertex has degree greater than 5, then what does it mean? It means that every vertex has degree greater than or equal to 6. Then the total degree will be what? The total degree will be, so So otherwise, we are proving this. Otherwise, the total degree will be greater than or equal to 6 times V. Am I correct? Because each vertex has degree at least 6 rather than 5. So if the total degree is greater than or equal to 6V, then it means that the edges is greater than or equal to the total. So the edges is equal to what? Number of edges must be equal to total degree divided by 2. So the edges will be greater than or equal to 3V. And then this is a contradiction, because the number of edges for a planar graph cannot be greater than or equal to 3V. Is that okay? So this is a key result that we need. So in any planar graph, we will have a vertex that has degree less than or equal to 5. Okay, so we start with this one to prove the 5. So that's why we have a 5-color theorem. So this is because of this 5. Is that okay? If you're okay with this, could you please raise your hand? Okay. And now, okay, what do we do? So we have a graph. This is a planar graph. And then we know that there is a certain vertex that is of degree less than or equal to 5. So let's call it V. Okay? So we are going to show by induction that all the graphs that is planar can be colored using 5 colors. Okay? Okay, so we are using induction. So induction tell us what? Okay, if a graph is very simple, it just has one vertex, then I can color it. If a graph has 2 vertices, I can color it. And assume that we have a graph that has very few vertices, we can color it. Then what happens if I have one more vertex? Can we color it? Can we still color it using 5 colors? Is that okay? So this is the point. So what we are going to do? So suppose that we have a graph that has n plus 1 vertex now. But what we know is we know that if G prime for any graph, but we know that, so we are going to use induction to show the 5-color theorem, but we know that for any graph, for any planar graph, with n vertices, we can color it using 5 colors. 5 colors will be okay. So now let us consider what happens if we have n plus 1 colors. So this is the idea. And then when we have n plus 1 vertices, when we have n plus 1 vertices, so we start with finding any vertex that has degree less than or equal to 5 to begin with. So let's call it V. So it has less than or equal to 5 as the degree. So we want to show that we can still color it using 5 colors. Is that okay? So if you understand what I'm going to do so soon, could you please raise your hand? And nobody? Okay. Yeah. So again, so what we are going to do, so the proof turns out to be very easy. But the process is a little bit complicated. So we are going to show a graph. If it is planar, then it is always 5. You can always color it using 5 colors. But what we are going to show is we use induction to help us to simplify the case. So this is the induction strategy. So we assume first of all that any graph with n vertices we know how to color. Is that okay? So what happens if we have n plus 1? So this is the key point. All the n vertex graph, I can color it. Then how about n plus 1 vertex? Okay? So now we just need to focus on n plus 1 vertex. And then when there are n plus 1 vertex, so first of all, we must always be able to find a vertex V, some vertex V, that has degree less than or equal to 5. Okay? Now let me tell you why this is something good for us. Okay? So first of all, if we can find a vertex V So this is a planar graph already. We draw it already in the planar form. If you find a vertex V that has only degree 3, then how can we color it using 5 colors? The answer is yes. Okay, because we first of all ignore this V. We have the whole graph here. Let's call it G minus V. So G minus V, the graph G, when V is deleted, it contains how many vertices? It contains n vertices only. Is that okay? So we can color it using 5 colors. Okay? We can color it using 5 colors. So once we have colored all the vertices using 5 colors, so maybe this is in red, this is in green, and then let's say this is in blue, then we can always choose another color to color it so that we can color the graph again using only 5 colors. Is that okay? Is that okay? So when the degree of V that we look at is equal to 1, 2, 3, 4, it is easy, even if there are 4 vertices. Maybe this is yellow. If V is only connected to only 4 different colored vertices, then it is okay, because there is always a 5th color for it to color. Is that okay? Is that okay? So this is an easy case for us. So what is a difficult case? What is a difficult case? The difficult case is when this vertex V is connected to 5 of them, 5 other vertices, then this is a problematic case. Is that okay? Okay. But notice that this is not always problematic. Okay. So I'll give you an example which is not problematic. Suppose we can have colors red, green, blue, yellow, white. Okay. These 5 colors. Or easy, RGB, red, green, blue, yellow, white. Okay. So maybe this is red, this is green, and this is red, this is yellow, and this is blue. Somehow, the coloring of the outer part, we do this by induction, that we can color it. But then, it's just using 4 colors. So the red is repeated. Is that okay? Then this will be a good case for us, because we can still color the V using the color white, the remaining color. Is that okay? Is that okay? So what is the most difficult case for us? The most difficult case for us is when the induction says, this is colored in white. Then there is a problem. We cannot directly use the induction result, the induction hypothesis, to color V, because all the 5 colors are now used up. Okay? Now, what should we do? The idea is very simple. We try to save 1 color. Okay, we try to save 1 color. So for instance, is it possible that we do not color this in blue? Okay, so this is the idea. Let's try to save 1 color. So let's try to change blue into green. Let's try to change blue into green. Okay, if I change blue into green, nothing happens. It's still okay to color outside part. Okay, with blue into green, then I can color this into blue. Is it okay? But what will happen? If I change this from blue into green, then what is the problem? The problem is that maybe there are some vertices joining to this one. It's colored in green originally. So if I change this from blue to green, then we have a green-green. Is that okay? Then what should we do? What should we do? What should we do? Change green into white? Okay, easier. Change green into blue. Is that okay? So we do green into blue. Is that okay? Now we have the blue here, but then we will have blue outside. Am I correct? So we may have a blue here. Then what should we do? We change blue into green. Is that okay? So it is like we start from this vertex blue, we change it to green. All the neighbors that is green, I change it to blue. And all the neighbors of blue, I change it to green. So if I can do this forever and then stops at some point, then it should be okay. Am I correct? But there is one problem. Okay, what is the problem? So if this is that easy, then you don't need 5 color theorem. You may have 4 color theorem. The most difficult part is that you have a blue here. You try to change it to green. Is that okay? Then you change it. You change it. You change it. So this is blue. to green, but then this is green to blue. Is that okay? And then this is blue to green, and so on and so forth. The problem is that you come back here. So that if you change this from blue to green, then this change from green to blue. Is that okay? And then we are doing something that is fruitless. Yeah. So we try to save a color by changing blue to green. But in the end, okay, good. This can be changed to green without any problem. But suddenly, you change this back from green to blue. So you are still not saving any colors. Okay? But then this is not that bad. Okay, this is not that bad. So for this to happen, there must be a path that is drawn on the plane that joins this blue vertex and green vertex together. Am I correct? And in that sense, then I can change this R to Y. Because what I know, R and Y cannot, there's no way that R and Y can join together. Because it is a planar graph. We cannot have any edge crossing each other. Is that okay? So if there is a blue to green path like this, it is not possible to have a R to Y path. Then in that case, I can change this R into Y and then save a color. So that's it. So I don't know, I think this is very interesting. Okay, so the idea is so simple that, okay, once again, let me recap. Let me summarize the idea. So you start with a vertex V, and the most problematic case is you have all the vertices joining to V are in different colors. So let's say this is red, blue, green, red, blue, white, yellow, and then green. Okay? So we try to find a way to save a color by changing this green into blue, and then there may be a problem. So if there is a problem, then we change. Okay, so this is green to blue. Then we can have this one blue, then we change it to green, and green to blue, blue to green, green to blue, and somehow we may join this back, blue to green. And this is the only case that we are not saving a color, because when this change from green to blue, this change from blue to green, we are still using the same number of colors. But in that sense, so this is already a graph that is planar. You are using the planar embedding. So in that sense, this R, there is no path joining from R to Y without crossing the edge. You cannot use the vertex here. So you cannot use the vertex here, because this vertex is either a green vertex or a blue vertex at the beginning. So when you are changing from R to Y, we are focusing on R-Y path, from red and yellow path. The red and yellow path cannot reach this Y. There is no way to reach this Y without crossing these edges. Is that okay? So in that sense, we can always safely change this R into Y, and all the neighbors of this one of Y into R, and so on and so forth. Okay, so everything appears in this part. So we have a very local change, a small change, and then we are saving one color. So we can change this R into Y. When this is changed into Y, then the color of V can be colored in the fifth color, the red here. Is that okay? Is that okay? So in that sense, if a graph with n vertices, you can color it with 5 colors, then a graph with n plus 1 vertices, planar graph with n plus 1 vertices, you can color it in also 5 colors. So that's the 5-color theorem. So easy, right? Very easy. So don't worry. Okay, every discussion on this Platonic solid and 5-color theorem are just for fun, and then I hope you like it. So this will not appear in the exam. But on the other hand, check the assignment. Okay, so the assignment will, I guess, it will ask you to check if a graph is planar or not. In that case, Kuratowski theorem, you still need to understand. Okay, so let's end the class early today. And then if you have any questions, please come and ask.